In the first two lectures on data analysis, we looked at one variable and two variable exploratory data analysis. Those were qualitative types of analyses. In this lecture, we're going to look at quantitative analysis. Specifically, we're going to look at hypothesis testing, which is one of two lectures on inferential statistics. But before one can understand inferential statistics, one must understand the central limit theorem. This had been mentioned briefly in a previous lecture, but now we're going to talk about what this theorem really means, and then we'll use it to make hypothesis tests, and in the following lecture we'll use it for confidence intervals for data collected from surveys. The central limit theorem provides guidelines for working with sampling distributions. And I have found with my statistics classes that to really understand the central limit theorem, one must understand what we are talking about. We say we're dealing with sampling distributions. Imagine a large barrel filled with colored marbles. 40% of the marbles are red. 60% of the marbles are blue. There are thousands upon thousands of marbles in that barrel. After the marbles are thoroughly mixed and you are blindfolded, you reach in and select exactly 20 marbles, strictly at random, without any ability to see which color the marbles are. An assistant counts the number of marbles, specifically the number of red marbles, records the proportion. So, for example, if 10 of the marbles were red, 10 out of 20 is 0.5. If one of the marbles were red, 1 out of 20 is 0.05. Your assistant records this proportion, throws the marbles back in the barrel, and stirs the marbles in the barrel up again. The pattern is repeated. You would reach in blindfolded, take 20 marbles. Your assistant would count the number of reds, write down the proportion, throw the marbles back in, stir the pot, stir the barrel. You would reach in again and again and again and again until you had thousands of samples. And for each sample, your assistant would have written down a proportion. Of course, those proportions would go from 0 if none of the marbles were red, through 1.0 if all the marbles were red, and the only values would be those that ended in 0 or in 0.05. For example, if you had 3 out of 20, it'd be 0.15, 7 out of 20, 0.35, etc. And what you would have is you would have a count for each of the proportions from 0 through 1, how many of the thousands upon thousands of the samples had that proportion. And when you wrote a chart or provided perhaps a histogram as a representation of that distribution, you would have the results of a sampling distribution, a distribution of sample events. In that particular case, the event was a proportion. So you have a sampling distribution of sample proportions. And we could look at that distribution and talk about its mean, that is the overall mean of all the distribution percentages. We could talk about the standard deviation, the measurement of variation of the various proportions. And we could talk about the shape of the graph, of the histogram perhaps, of the distribution of sample proportions from your sampling distribution. The CLT, central limit theorem, addresses these things: the mean, the standard deviation, and the shape of the distribution. Pierre-Simon Laplace, a French mathematician, was the first to work on the central limit theorem. His work began in 1810. You'll notice from the picture, he probably received a medal for the fine work he did on this theorem. The central limit theorem requires that the samples are randomly selected and that are all the same size, no matter what the shape of the distribution of the population from which the samples are drawn. As the sample size increases, the sampling distribution approaches the normal distribution. The expected average value for all the samples is the population parameter. A statistic is from a sample, a parameter is from a population. And symbolically that says the expected average mu of x bar equals mu. The mu of x bar is the average of all the sample means in a distribution of sample means. The mu by itself is the population mean. This makes a great deal of sense. If you were to take all the students at a particular elementary school and measure their heights and obtain the average height, the mean height of all those students, it would be the same as taking groups of 5 students, measuring the average of those 5 students, and then averaging all the averages. You'd get the same number. So the first step in the central limit theorem makes a great deal of sense. And if we're looking at the distribution of proportions, we have the next expectation equation, which says mu of p hat equals p. The mu is the average or expected value, the average for all the sample. P hat is the sample proportion, the estimate of p. P is the population probability. So it says that if you're doing a sampling distribution of proportions, that the average of all the sample proportions in your distribution would be equal to the population proportion or population percentage or population probability. Now, we talked about the average. We need to worry about the measurement of variation. And in terms of variation, the standard error, which is the standard deviation of the sampling distribution, the standard deviation of all the measurements from all the samples. In this case, sigma x bar, the standard error for the sample means, sigma sub x bar, is equal to sigma, the population standard deviation, divided by the square root of n, where n is the sample size. Remember that the CLT requires all the samples in one distribution to be of the same size. If we're looking at a distribution of sample proportions, the standard error is sigma p hat, and that is equal to the square root of pq over n. P is the population probability of success. Q is 1 minus P, or the population probability of failure, and N is the sample size. Again, each sample in that sampling distribution is the same size. So we have a declaration in the theorem about the mean of the sampling distribution and about the standard deviation or standard error of the sampling distribution. And the hypothesis test uses these 2 items. But also, we must be concerned with one more thing, and that is that the central limit theorem tells us that the distribution of the sample means or sample proportions approaches normality. And we'll talk more about this later on. So, let's go and take a look at how we do a hypothesis test. An hypothesis test begins with a statement of the null hypothesis. And the null hypothesis simply is a statement that there is no significant difference. There is no significant increase or no significant decrease or simply no significant difference. The symbol for the null hypothesis is capital H sub 0, hypothesis sub 0. And this is the beginning of our test of hypothesis. This is not necessarily the hypothesis we believe. This simply says there is no difference. The hypothesis that is generally believed by the person doing the test is the alternate hypothesis, H sub A. And this says there is a significant increase, if indeed you believe there's an increase, or there is a significant decrease, if you believe there's a decrease, or if you're simply looking for a significant change, the alternate hypothesis would say that there appears to be a significant difference. The null hypothesis is used for testing, we know the population parameter required by the CLT. What is that? Well, if we're looking at means, the CLT requires that we know the population mean, mu, and the population standard deviation, sigma. If we're testing a hypothesis on proportion, the CLT requires that we know the population probability of success, P. And of course, therefore, we immediately know Q. And remember, I'll repeat again, that all the samples in the sampling distribution have to be the same sample size. In actuality, when we do a hypothesis test, we'll only have one sample. But theoretically, we could have drawn millions of samples of that same sample size. It is assumed in our hypothesis test that the null hypothesis is true. The sample data is evaluated to see if the result from the sample contradicts the null hypothesis, that there is no significant change. Since the central limit theorem states that assuming we have a large enough sample, that is, our sample size is large enough, the sampling distribution is approximately normal. We use the standard normal, or Z table, to measure the distance from the sample statistic, from our single sample, to the population parameter, which would be mu or p, depending on whether we're looking at samples of means or samples involving proportions. Now, if the original population is known to be normal, then the sampling distribution itself is normal. But in most situations, as long as we have a large enough sample, and statisticians generally would use a number that they would determine to be large enough sample, you could have a situation in which you would use the normal table, the Z table, the standard normal table, to do your computations, as we did in our previous discussion of the normal distribution. So the key thing that the central limit theorem tells us in terms of the null hypothesis and hypothesis test is that if we're doing a hypothesis on a sample mean versus a population mean, that we have an approximately normal distribution, close enough to normality that we can use the normal table. We know the mean of the population, and that is to be the mean of all the sample means if we took the millions and billions of samples available. The standard error, the sampling distribution standard deviation for the distribution of means, a hypothesis test on the means, would be sigma over the square root of n. If we're doing a hypothesis test on a proportion, again, the central limit theorem would tell us that we could use the normal table, the Z table. It would say that the expectation for the average of all the sample proportions would be p, the population probability, and that we could find the standard error of the sampling distribution, this normal distribution, and it would be equal to the square root of p q over n. Given that all the things we need are known, we can simply use the Z table to determine if the sample statistic we have, the x bar or the p hat, is far enough away from the expected value, that is the mu or the p, to indicate that the result we got is either rare for a situation where the null hypothesis, no actual difference, is true, or the null hypothesis is contradicted. And again, what I'm trying to do here is simply give you a picture of what hypothesis testing is all about. I do not expect everyone who watches this lecture to run out and begin to do hypothesis testing. Obviously, you need to take a course on inferential statistics, and probably, to do it right, take 2 or 3 courses or read a number of books. This is just to whet your appetite in terms of understanding what is going on when, for example, a drug is tested, and that is a hypothesis test, or a school system tests a new method of teaching some subject matter, or a corporation tests an incentive program to see if it can increase production by offering particular incentives to its employees. But more on specific application in a moment. Let's go back to how we are doing this hypothesis test. We compute the Z-score, and the Z-score is computed by dividing the difference between the actual minus the expected value, that is the x bar, which is the sample mean, minus mu, the expected average for all the sample means, divided by the standard error. Or if we were doing proportions, that would be p hat minus p divided by sigma p hat. But the key thing here to notice is the z is always the actual minus the expected divided by the standard error. We are touching on only two types of hypothesis tests. There are many types of hypothesis tests, but when you're using the z-table, it's always the actual minus the expected divided by the standard error. We look at the z. The z tells us the number of standard errors our sample statistic is from the expected population average. And therefore, we can go to the z-table and find the probability of obtaining a sample, assuming the null hypothesis is true, that is, there is no difference, of that much difference or less. And by taking 1 minus that, we can find the probability of getting that much difference or more. If the probability, or p-value, of getting that much difference or more difference is a very small number, then the probability of getting the result we obtained simply by chance, assuming that the null hypothesis is true, is a rare occurrence. Most likely, the reason for the significant difference between our sample result and what we expected to get is that the null hypothesis is not true, that there is a significant difference in our sample and the population. To truly understand this, we need to look at least one application. Now, let's take a look at a situation that involves an hypothesis test on p-hat. A newspaper claims that 40% of the population favors a tax increase. This is a headline on the front page. A sample of 100 randomly selected citizens is asked their individual opinions about the tax increase. Only 30 support the tax increase. The other 70 do not support it. So here we have, symbolically, the data. We have a p, a population probability of 40%, or 0.4. We have an n, a sample size of 100, and an x of 30, x being the number of successes, a success being a person who responded, yes, I favor the tax increase. And therefore our p-hat, which is x over n, is 0.30, or 0.3, which, of course, is less than the 0.40 the newspaper claimed. What is our alternate hypothesis? Our alternate hypothesis is that the percentage of citizens who favor a tax increase is significantly less than the 40% stated in the headline in our newspaper. We do a test of hypothesis by taking the three numbers, the actual sample information, which is 0.30, the expected outcome, which we expect to average 0.40 when we, assuming the null hypothesis was true, and the standard error, which is computed using sigma p-hat equals the square root of pq over n. And of course, we then take our z-value, p-hat, minus p0 over sigma p-hat. Of course, now we complete the formula with numbers. Z equals 0.30 minus 0.40 over 0.049. That 0.049 is the standard error, and it was obtained by multiplying 0.40, the p, by 0.60, the q, dividing by n, 100, and taking the square root. The z value is negative 2.04. Why is the z value negative? Because our result, our sample result, 0.30, was less than our expectation. We are to the left of the mean of our normal distribution, and we have to have a z that's negative. The question is, how significant is that result? We look at our z table, and in our z table, looking up for a z of negative 2.04, we find that the area, or the probability to the left of that z, is approximately 0.02. Now, what does that say? That says if the null hypothesis is true, that indeed there is a 40% of the population that favors the tax increase, that obtaining a sample of size 100 that had a proportion, a p-hat, of 0.30 would occur about 2% of the time. Is this a rare occurrence? Yes, indeed. Recall in an earlier lecture, I mentioned that most statistical investigations use 0.05 as the largest of the probabilities of, in this case, from the Z table. So we have what's called a level of significance of 2%. That 2% represents the probability of getting a sample result that we got or further away from the expectation. That is, getting a sample proportion of 30%, 0.30 or less, given that the null hypothesis is true, simply by random occurrence. Because in a normal distribution, we'll have 2% of the samples that will be that far away. That is 2.04 standard deviations below the expectation, below the 40%. And since that 0.02, that level of significance, is rather small, we say this is a rare occurrence if the null hypothesis is true. And most likely, the null hypothesis is not true. We cannot say that the null hypothesis is definitely not true. Statisticians never talk in certainty because we're dealing with probability. A statistician would say there appears to be reasonable evidence to indicate that there is a significantly lower percentage than 40% of the populations of citizens who favor a tax increase. The people at the newspaper who claim that 40% is correct would say, we just got lucky and we got one of those small number of samples below 40% and far enough below 40% to be only a 2% chance. So the fact is, no one can ever argue. You can never get a result that is guaranteed. No matter how many standard deviations you are below the mean, there's always a chance. 1 in a million, 1 in a billion, 1 in a quadrillion. But there's always a chance that you can get a sample, theoretically, that far away. So in this particular case, the result is such that we would indicate that chances are the population percentage of people who would support the tax increase is somewhat lower than 40%. Not guaranteed to be 30%, but certainly it would appear not to be 40%. And that is a hypothesis test on proportion. Let's look at a hypothesis test on sample mean. A manufacturing plant is involved in testing an incentive program, and they need to evaluate this program, let's say at one or a few plants, before they use the program in all their plants. So what they must know about is the hypothesis test on the sample mean. What we must have to do this is a sample mean, x bar, a population mean, mu, or sometimes called mu zero, the population standard deviation, sigma, and the sample size of our one sample, that is n. And we find the standard error by finding sigma x bar equals to sigma over the square root of n. Once we've done that, we'll find z by saying z, of course, is what we obtained from the sample minus the expected, that is the actual minus the expected, over the standard error. In this case, x bar minus mu over sigma x bar. And then we'll determine the level of significance, the probability, from our Z table. Let's take a look at the manufacturing plant's situation. They had an average daily production of 30 vehicles per production team. And the standard deviation for these production results was 10. So we have a mu, or mu zero if you like, of 30, and a sigma of 10. A random sample of 25 teams was allowed to participate in a trial incentive program. In other words, the teams that were selected were not selected with the most senior members, the best workers, the ones with the fewest absences. We randomly selected 25 teams. And by randomly selecting, we should have a situation where some of the teams might be very good and very productive, and their production is better than average, and some teams whose production is lower than average. In fact, before we can do a real hypothesis test, we'd have to have another course on designing a sampling experiment. And that gets quite involved. And in fact, as we saw, we talked about simulations, the design process is really quite important. But in this particular case, if we were managing this plant or running the company, we would hire some statistician who was an expert to come in and design this particular experiment. And indeed, it is an experiment because we are applying a treatment to the sample. In this case, the treatment is the trial incentive program. We look at the performance once we start the trial incentive program, and we measure the average production per team. And we get a figure of 35 vehicles for the 25 teams. That is, the teams average 35 vehicles during the daily production, during the time when they were under the trial incentive program. The null hypothesis would say that no matter what you do, any kind of incentive program you use, the actual average production per team would continue to be 30. There is no increase in the production because of the trial incentive program. The alternate hypothesis would say, no, we believe there is a significant increase in the average production per team for teams that have been given the opportunity to participate in this incentive program. So once again, we have to get our Z, and our Z would be 35 minus 30, that is X bar minus mu, our actual minus expected, divided by 2, our standard error, sigma X bar. That is a Z of 2.50. Notice that Z is positive, because again, since we actually had an increase, our X bar was greater than mu, we are to the right of the normal distribution, and therefore Z is positive. This says that our result, our sample result, is 2.5 standard errors above the expectation, above the mu of 30. We go to the Z table. We look in the Z table for a Z-score of 2.50, and the level of significance we obtain is approximately 0.006. In actuality, when we go to the table, we get the probability of obtaining a score of 2.50 or less. That is the area to the left of 2.50, and that will be approximately 0.9940. We subtract that from 1 and get our 0.006. What does that 0.006 mean? It says that there's probably about a 0.6% chance of getting a result this far away, that is 2.5 standard errors above the mean of 30 or higher, if the null hypothesis is true. The null hypothesis says the incentive program doesn't cause an increase. 0.006, 0.6%, sounds as if it's a very rare occurrence. If something happens 6 times out of 1,000, that is quite rare. But again, the statistician would not say, nope, the null hypothesis is not true. We guarantee you that we will have an increase in production if we have this incentive program. What the statistician says is there appears to be significant, in fact, strong evidence that we can obtain a significant increase in average team production if teams are allowed to participate in this incentive program. There are no guarantees in statistics. I should mention that at times, instead of looking at a sample statistic versus a population, that is X versus mu or P hat versus P, we look at the difference between 2 sample statistics, X bar 1 minus X bar 2, or P hat 1 minus P hat 2. This is used when you have no population figures. And to do that, that is a whole another process similar to this, but it uses a table, in many cases, different, somewhat different, than the normal distribution table, the z-table. But that is for another lecture series. Suffice it to say, we've had a brief glance at what hypothesis testing is, whether it's used to evaluate incentive programs, prison reform programs, education programs, new drugs or methods of medical treatment. It is a hypothesis test, and you go to the z-table and we obtain a probability and we recognize whether we have a significant increase, a significant decrease, or not. In our next lecture, we will talk about the other type of inferential statistics, surveys and confidence intervals.